So now you're going to become advanced learners in atomic absorption because we're going to go back and we're going to revisit a piece that we need to talk about in more detail. Okay, so what you saw before in a previous video when we talked about a light source, we just basically explained the light bulb itself, and we said that you have to have a bulb for every metal, and that has a particular wavelength that gets shown into that gets directed into the sample, and that sample begins to absorb, and the detector picks that absorption up. All right, so here's the problem. The light source doesn't just give one wavelength. All right, so the light source can actually give multiple wavelengths. And you're probably now scratching your head saying, well, this doesn't make any sense. Well, bear with me for just a second. When we run copper in the AA, we have said that copper has a wavelength that it really likes. And the purpose of the light bulb is to give copper the wavelength that it really likes. And the bulb does do that. There's no difference in what you've learned so far. So copper has a preferred wavelength. And that preferred wavelength is what we call the primary wavelength. And we abbreviate that with a 1 and a little circle up above. So copper has a preferred wavelength that we can give it, and this primary wavelength is the most sensitive. Now, we're calling it the most sensitive because if I'm doing analysis on copper, I want the machine to be tuned into copper, and I want copper to be analyzed. And if there's a small, slight difference in copper concentration or how much copper is there, then I want the machine to be able to tell me, and I want it to feel good about the number that it's going to represent. That's the purpose of the primary wavelength. So I choose copper. I put the copper bulb into the machine. I dial it in to the proper primary wavelength for copper, and the machine will start making the measurements. But if you go back a couple of videos and you look at when we describe the absorbance and the emission spectrum, what you'll see is that some of these colors absorb light, and they absorb multiple lines of the spectrum. Now, this is basically the emission. These are the colors that are given off. So you've got to think of this backward for absorption, but it's going to convey the same concept. If I look at neon, neon has multiple bands of light that's listed on its emission spectrum. I see them. They're all here. That means that neon bulb, if I'm trying to measure neon, actually has multiple wavelengths that I can do my analysis at, right? If it absorbs at each one of these locations, then I have multiple choices of where I can go and make my measurements. Now, there's going to be one of these colors that's going to be the best for that specific metal. But if there's a problem with that one for some reason, I can move on to a second or a third or a fourth or a fifth color that I can do my measurements at. Well, if you look down here at iron, for sake, I look at iron and I see multiple wavelengths that are there. There's tons of them. One of those is going to be the best, and that's typically where I would make my measurements. But there's going to be a handful of others that are present. I mean, I see all of them. They're right here. All of these iron will absorb. But Not all of them are going to be important. And sometimes I can't pick the best one. I have to settle for second best or third best. So now you're probably questioning, well, why, right? Why can't I use primary every single time? Why would I have to go to the second best wavelength or the third best wavelength? Well, remember this slide. Tons of lines for every single metal. That means tons of wavelengths that I can choose from for each one of those metals. I'm not just limited at one. One is the best for each metal, but each metal will also come with other choices that I could pick from. And that's why those are present, because they absorb multiple wavelengths, not just one area that they absorb from. They absorb in many different places. So the primary wavelength is the most sensitive. So that means if I have very weak concentrations, and typically for atomic absorption, that's parts per million. And parts per million is ppm. Tons of choices for my copper. It absorbs multiple places. Primary is the best because it allows me to measure very weak solutions. This is the most sensitive that's out there. And when I'm working on a 1 part per million, 2 part per million, 1.5 part per million level, that's really, really tiny. So primary is going to be the best for me. So here's the thing. What if I don't have weak solutions? What if I've got maybe a mid-range? They're a little strong. Well, if they're a little strong, then the primary might not be the best for me. And now you say, well, why? Well, the problem here is this word called linearity. Linearity basically refers to a calibration curve. When I make a series of standards and I plot those standards, I want to see a straight line that shows up in my calibration curve. That r squared better be close to 1. Well, the problem is that with most of these primary wavelengths, primary wavelength does a very good job in the lower part of the calibration curve. Remember, this is super sensitive. It can distinguish the differences at a very, very tiny level. But the problem is that sooner or later, I'm going to be above the linearity range. And let's say that that linear range is going to be here. Well, the primary begins to get overwhelmed. The sample becomes so concentrated that it cannot determine the differences between them. So if I'm giving it a 10 part per million or 20 part per million, it can't distinguish the difference between a 20 ppm and a 22 ppm. And it begins to get some problems. And that's what we call the linearity range. Well, these problems will start to make my linear curve non-linear, and it will start to bend. And I don't need that to happen in a laboratory, maybe. So there's a couple of ways that I can fix this. One of the ways that I can fix it is I can dilute the sample. And I can dilute the sample to get a very small concentration that would work on the primary wavelength. As long as I'm not out of that linearity range, as long as I'm underneath that concentration level, then I can feel good about the data. But if I have a concentrated sample that's outside of the linear range, primary is not going to work for me. And one of the ways that I can fix the problem is to take the sample and dilute it. And when I dilute it, I can rerun it, and then it will tell me the concentration. I just have to go back and then recalculate for the corrected concentration. So that requires a little bit of extra math, right? After I get the concentration, I'm going to have to do a little bit of extra math called a back dilution, because I've taken the sample and I diluted it in order to run it. So then I have to go back and refigure what that concentration is because I diluted it in order to run it. Well, some people don't want to go through all of that mess. Some people just want to say, listen, I know that my sample is concentrated. I don't want to go through the process of diluting everything and then reworking all of those calculations to see what the original concentration was. I just don't want to do it. So the second choice is to choose a different wavelength. Choose another wavelength. And you know, that doesn't make any sense, does it? That wavelength needs to be nanometer, and that is the symbol for wavelength. Okay, if we choose another wavelength, we don't call it the primary wavelength. There is a second best option that's available to you for some of these atoms, and that's what we call the secondary wavelength. So I'll put a 2 with a little dot up above it. That means that this is not for the most sensitive. This wavelength should not be used for the really low levels that I need to measure. But this wavelength can be used for maybe mid-range concentrations. But yet again, the secondary has its limitations as well. All right? So the secondary is not as sensitive. The secondary can still measure in part per million. That's going to be okay for it. But the secondary will allow higher concentrations to be analyzed versus the primary one. So maybe I've got a 20 and a 30 and a 40 part per million sample, and maybe all of the samples are that way, and I don't want to dilute every single sample in the laboratory because then we could be talking about 40, 50 samples here. So the choice now becomes very clear. I just now need to go into the machine, and instead of choosing the primary wavelength, I choose the secondary wavelength, and I just run everything as is. And the secondary wavelength will expand maybe the linearity range. The problem is that this secondary, right, can't go very low, because that's the purpose of the primary. If you're thinking Goldilocks, one porridge was too hot, one porridge was too cold, one porridge was kind of in the middle. This secondary wavelength is kind of in the middle. So I'm going to draw two pink lines here and here. And this represents the area of the secondary wavelength. Linearity is evident, but linearity is only typically in mid-range. That means too high, it won't work. And then too low, it won't work. But it does a very good job in the middle. Now, if you compare that to the primary wavelength, the primary will do a very good job at really low levels up to a certain point. And this primary wavelength should be used when we have very low concentrations. But this is not the only wavelength that's out there, because we can have tertiary wavelengths, quaternary wavelengths. These things can go on upwards. 5, 6, 7, 8, 9 different choices of wavelengths that I could make my analysis with. The problem is that typically, as you go up from primary to secondary to tertiary to quaternary, it allows you to measure higher concentrations. But you cannot measure low concentrations. And that's the purpose of having multiple wavelengths that you can make your analysis with. So an analyst in a laboratory would look at the setup, and they would have to have an understanding of the sample. How concentrated is the sample that you're given most of the time in the lab? And if your job is to analyze 20, 30, 40 samples at a time, no one is going to go through the process of diluting every single one of those. So what we do instead is that we switch the machine over to a secondary wavelength, or a tertiary wavelength, or a quaternary wavelength, and we make our measurements at that spot based on our concentrations that's expected. So primary wavelength is typically what's preferred. Primary wavelength is the most sensitive. Primary wavelength will allow me to go to really low concentrations and do my work. But secondary, tertiary, quaternary, and on up is present. And it's there for you if you need to use it. And the reason you would use it is because you have gotten samples that are more concentrated than what the primary can handle. Okay, so that's the story with the light bulb. That's the story with multiple wavelengths. And that is a setting and a decision that you have to make as an analyst when you're working in a laboratory. What do you pick? Well, primary's preferred every time. But if your samples are concentrated and you've got a lot of them, you need to get away from the primary, and you need to go through and take a look at secondary, tertiary, quaternary, and so on. Keep in mind that each of the wavelengths, primary, secondary, tertiary, will have their own slit width. Now, sometimes they're the same when you go from one to the other, but sometimes they change. So when you change your wavelength, you have to double check the slit width in order to do that. And every time you change the slit width, you need to come back and you need to align the lamp again, because that slit width can have an effect on how the light reaches the detector. So if you're changing slit, you've got to realign the lamp every single time. Okay? So, just a couple of things to be forewarned about. There's one of them. It's called the light bulb choice. What do you choose to analyze your poison?